Now, if you clearly see the algorithm, for this purpose, for implementing Prim's algorithm, we are taking the help of priority queue for the same. Now, for priority queue, what special we have to do in this case? We have to first initialize two tidbits we have to take for this set of vertices. One is the distance, or you can, some books do say key values for the vertex, or the parent, or also called pi value of the vertices. You can choose any of the notation you want. We initialize every vertex key value to infinity, and the predecessor or parent of every vertex as null. These are the two statements for every vertex in the graph. We have to settle down both the values to infinity and null. And the starting vertex, whatsoever you are choosing for your Prim's algorithm, you initialize its key value or d value, whatsoever term you want to use, as 0, distance or key value equal to 0. Let us suppose starting vertex is a. We have you starting from the vertex a, we initialize a key value or d value equal to 0. Now, after this, we have to create a priority queue, and after building for all the vertices in the graph, create a priority queue. Let us first priority queue contains all the values which is being created based upon, that is called min heap structure, minimum priority queue. Minimum value is being taken the highest priority, and this is based upon the key values. Now these are the values of the priority queue. A has got key value 0, B is infinity, remaining are infinities. So what we have to do in next? In this case, after A has been chosen, find the minimum. Once you have got, repeat this step n times. What we have to do, because we have to go for n minus 1 edges when you are repeating it n times. So we have to find the extract min function or remove min function. Extract min will extract this vertex A out of this. So once extract min function is being called, this is the final set of vertices. Result will be stored. So this A vertex, what it will do, before this A is being removed, let this A is taken as M vertex. This is being removed from the queue, priority queue, and this is added to the final answer T. Say, added to T, and for every vertex which is adjacent to M and which is not in A, which is not in T, जो T में नहीं है, so what are the adjacent vertices? Direct adjacent vertices, that is B, and the remaining vertices which were there, that was B, and another adjacent vertex was C, D, and another was F. Change the key value of that depending on the edge weight. That means if the cost of V comma M, if the cost of V M is A, B comma A, if it is less than distance of V is infinity. If this edge weight is smaller than this key value, then update this key value to the edge weight of that. So this will, B will become equal to 2 here, and D also is, AD is distance is 17. This will also become, earlier it is infinity key value, this will also be updated to dB is equal to cost of VM, that is edge weight, that is 17, and even F will also be updated to 16. And because of this A, these values have been updated, the predecessor of pi value or parent value of B will become equal to A, D will also become equal to A, and this this F will also become equal to A, like this. That means the key values of B, D, and F are updated. After this, again apply. Now this has been removed, A has been removed. Now again go for the minimum value. Priority queue will again extract the minimum value based upon the key value. Now because we have updated B is equal to 2, D is equal to 17, and F key value now has become 16. Based upon the key value, B has got smallest value. Now B will be added to the, because B has got smallest value, B will be added to the final set T, and try to find the cost of the direct edges adjacent to B. Direct edges adjacent to B which are still not a part of T are C and T. If you carefully see, C is earlier key value having infinity, but the edge weight of B and C is 15, so you will update this as 15. Similarly, BD distance was earlier the key value of D was 17. Now because BD is 5, this distance will also be, key value will be also updated to 5. So these both the things are being updated, and when C value is being updated, and that of d value is also being key value is also being updated. Because b is removed from this priority queue, the next smallest chosen vertex will be now d. Now in this case of D, again try to figure out, so D will be a next time part of this final T vertex answer, and try to figure out all the vertices which are adjacent to D but not a part of this T final T. So these adjacent to vertices are F and E. If you carefully see, the key value of E is infinity. Now this will, because 8 is less than infinity, this will be this key value will be updated to 8. Similarly, going to D to F, the distance weight is 9. Earlier the value was greater than 9, so this 16 will be updated to 9. So both the things will be updated and D will be removed from the priority queue. After removal of priority queue, the next minimum uh, uh, key value element is 8. Remember this thing? Simply parallelly we are updating the parent or the pi value of the given the vertices which are being updated. Now E is being used. Now for E, D has become a part of this. For E, adjacent vertices are C, which is there. Adjacent vertices D, we can't choose this because it's already part of T set. Adjacent vertices F. If you see for E to C, the key value is 13, but the edge weight is 11, so you can make it here 11. E to F, the edge weight here given is 9 but 12, but the earlier edge weight key value is 9, so no change in the F value for the same. So if you carefully see, the just C has been updated 13 to 11, no change in the remaining, and E has become a part of the final set T now. Now E is being removed. Next element which is to be removed from the vertex F is with key value smallest is F. So F adjacent to F which are not a part of T, A which is already part of T, D which is already part of E, and E which is already part of E. So nothing will happen, it will just remove from the priority queue. Next element is C. C, every element remaining no vertex is now part of this T. Again, no, nothing will be updated. C will be directly added to the final Prim's algorithm. Now the final output we can fetch from the predecessor graph, predecessor array, or the you can say pi array, whatsoever the name you want to give to this. Now how to go for this? A doesn't have any predecessor, so we will ignore this entry. AB will be one edge. A predecessor of B is A, parent of B is AB will be one edge. Then comes CE entry. So CE entry is there. So CE will be another edge. A predecessor of D is B, so DB will be one more edge. Then predecessor of ED, E is D, so ED will be one more edge again. Then predecessor of F, that is D, then FD will be one more edge. So this completes your minimum spanning tree. What is the cost of this minimum spanning tree? Sum of edges 2 plus 5 plus 8 plus 9 plus 11, that is equal to 35. Now the final output we can fetch from the predecessor graph, predecessor array, or the you can say pi array, whatsoever the name you want to give to this. Now how to go for this? A doesn't have any predecessor, so we will ignore this entry. AB will be one edge. A predecessor of B is A, parent of B, so AB will be one edge. Then comes CE entry. So CE entry is there. So CE will be another edge. A predecessor of D is B, so DB will be one more edge. Then predecessor of ED, E is D, so ED will be one more edge again. Then predecessor of F, that is D, then FD will be one more edge. So this completes your minimum spanning tree. What is the cost of this minimum spanning tree? Sum of edges 2 plus 5 plus 8 plus 9 plus 11, that is equal to 35.